Hello, my lovely AP Chemers. Today we're going to talk about solution stoichiometry. So these are stoichiometry calculations, but in reactions where they are done in usually in solutions, which means like in water, aqueous solutions. And a lot of times these reactions you do as a titration. So let's talk about titrations a little bit. So a titration is a lab technique where you have a known substance with a known concentration and you use it to react it with something that is unknown, and you use the known so that you can figure out the concentration of the unknown typically. And you basically react the two together until you've reached the equivalence point. And the equivalence point is the point where exactly enough titrant has reacted with the analyte. The analyte is what you're analyzing. The titrant is the one that you know information about, you're known. And so when both of them have reacted with the exact correct stoichiometric ratios, that's when you've reached your equivalence point. So you want to run this titration or this reaction until you've reached the equivalence point. And it's important to know when you have reached that equivalence point. Typically, there are two types of titrations or two types of reactions that we do titrations with. So the most common one is acid-base titrations. And so with acids and bases, it's very easy to put an indicator in there, and the indicator will change colors when you are near that equivalence point. So you can tell when to stop your reaction. So basically, one of your substances sits in a Erlenmeyer flask, the other one is in a burette, and you open up your burette and you dispense little by little until you see usually a color change that is caused by that indicator, and that tells you when you've reached a certain pH, which tells you that you've neutralized it or whatever. The other type of titrations is when you have a redox reaction where the oxidation state of one of the species is different in the products than it is in the reactants. So a lot of times some of the elements that have different oxidation states are one color in an oxidation state and a different color in another oxidation state. So when you see a change in color based on their oxidation state, that will tell you when you have reached the equivalence point. So a couple of redox reactions where we see them pretty common on the AP exam that they do a titration with are this iodine reaction, where you take iodine and you reduce it to I-. And usually when this reaction happens, the iodine color changes to like a pale yellow. And usually what we do is we add starch to it, and the starch makes the I- turn black or blue, kind of like a dark blue color. You probably have sort of looked at a reaction like that where you take iodine and starch, maybe in biology or in middle school or something, and it turns a blue-black color. So that's when you know your titration is over, you've reached the equivalence point, is because of that color. Another one that's pretty famous or common is this permanganate ion, where the manganese here is +7, is a purple color. If you remember my very first demo that I did for you was my grape Kool-Aid turning into water and then turning into milk. So that was the potassium permanganate solution. So the permanganate here has the manganese +7, which is a purple color. You can reduce that manganese and turn it into Mn2+, and the Mn2+ is colorless. And so that's what I did with my grape Kool-Aid demo, is I took some potassium permanganate, added a reducing agent, and the manganese reduced from +7 all the way to +2, so it turned from purple to colorless. So that's another one where you can tell based on the colors where your equivalence point is. And so usually we stop the reaction when it's like a very, very, very slight pale pink. That tells us that it's right at the equivalence point, because if you add like one more drop, it's going to turn completely colorless. All right, so let's do some problems with solution stoichiometry. This first one is not really a titration, but it is a solution stoichiometry problem. It says how many grams of zinc metal are needed to react exactly with 50 milliliters of a 0.25 molar solution of hydrochloric acid. So as usual, when we see a problem like this where it talks about a chemical reaction, we probably want to write out our reaction first. So we have zinc metal reacting with hydrochloric acid, so we're going to write zinc plus HCl. And they don't give us the products on an AP exam. They probably would, because you're not responsible for knowing how to predict products, but this is a single replacement reaction. So the zinc comes in, kicks out the hydrogen. Now hydrogen's all by itself, and then you form zinc chloride, which is ZnCl2. To balance it, you need a 2 right here. We know that we have 50 milliliters of 0.25 molar solution of hydrochloric acid. So 50 milliliters, I'm going to go ahead and change that to liters, 0.0500 liters. And then we have 0.25 molar. And if you remember in honors chem, I told you can either write it as 0.25 big M, or you can write it as 0.25 moles per liter, depending on how you like to do this problem. And then we are asked for how many grams of zinc are needed. So remember, with any stoic problem, there are 3 steps. You want to first find the moles of the substance that you have information about. So the only substance we have information about here is the HCl. We have enough information to find the moles. Then you find the moles of the substance that you want, which would be the zinc, and then you switch to grams. So first step is to find the moles of HCl. There are 2 ways to do it. One way is to do a different color here, is to use your molarity equation. So you say molarity is equal to moles per liter. So we're going to do this for HCl. And the molarity is 0.25 molar. It's equal to X moles of HCl over 0.0500 liters. And that will give you the number of moles. Let me go ahead and calculate that. Oh, where's my calculator? Oh, I guess I didn't need the calculator. Half of 0.25 is 0.125, and you just add a 0 there. But so you got 0.0125 moles of HCl. Then you can, and if you're going to do it this way, you probably want to write out your molarity with the big M like that. Then you find the moles of zinc. So you go moles of HCl, moles of zinc. Use your molar ratio 2 to 1. And then you go from moles of zinc to grams of zinc. 1 mole of zinc is 65.4 grams. Okay, and you get 0.41 grams of zinc, and that's your answer. Now let me show you another way that I prefer to do it, where just the first step is different, the rest of it is the same. So I like to write my molarity this way, as moles per liter. So to find the moles of this, instead of using the molarity equation, what I'm going to do is I'm going to start with my volume here, 0.0500 liters of HCl. And I'm going to put liters of HCl on the bottom so they cancel. I'm going to put moles of HCl on top because that's what I'm looking for. Oh, it doesn't like it when I write it on the, oops, in the middle there. Let me erase this. Sorry, I'm having technical problems here. Let's try and erase. There we go. All right. Let's try this one more time. So we have 0.0500 liters of HCl. We're going to change that to moles. So liters on the bottom, moles on top. And to go from the volume to moles of a solution, you use the molarity, which is right here. So this says 0.25 moles per liter, which means 0.25 moles for every 1 liter. So I'm going to put 0.25 next to the moles and 1 next to the liters. That way, I get my moles. And then the rest of it is the same as above. So then I'm going to go from moles of HCl to moles of zinc, 1 to 2, and then I'm going to say for every 1 mole of zinc, there are 65.4 grams of zinc, and you get your same answer. The only thing about this, I like this because I can see my units cancel. I know that I did it correctly. And then also I don't have to stop in the middle to calculate something. I can just do one whole calculation altogether. Both are totally fine. If you prefer the bottom one, the red one, then you write your molarity this way. If you prefer the blue way with the molarity equation, then you write it as a big M. Okay, let's try our next problem here. It says, what volume of 10th molar sulfuric acid solution is needed to neutralize 25 milliliters of 0.350 molar KOH? So we are going to write our balanced chemical equation. So we have H2SO4 reacting with KOH. This is a neutralization reaction, a double replacement reaction. So my H and OH get together to form water. And then my middle two get together. I have K plus and SO4 2 minus, so that would be K2SO4. All right, let's balance it. So I need 2 of these and 2 of these. I'm given that this is 10th molar, 0.100, and I'm going to write it as moles per liter, but you can write it as molarity if you'd like a big M. I am looking for the volume, so I'll put question mark liters or question mark V, and I know that this is 0.350 molar. Again, I'm going to write it as moles per liter, and I'm using 25 mils. I'm going to change that to liters, so 0.0250 liters. All right, so like any problem in stoichiometry, you find the moles of the substance you have information about, then the moles of the substance you want, and then answer the question. So I have information about this one, so I'm going to try to find the moles of the KOH. Same 2 ways. You could say molarity is moles per liter. You have the molarity, you have the volume, so you can solve for X or X moles. I like to use this way where I write out my units, so I'm going to do that. So 0.0250 liters of KOH. Change that to moles, so liters on the bottom, so they cancel. Moles on top, because that's what I want. And this is telling me it's 0.350 moles for every 1 liter. So 0.350 moles for every 1 liter. Okay, right now I'm at moles of KOH, so now I'm going to go to moles of what I want. So moles of KOH on the bottom, moles of what I want, which is the H2SO4 on top, and I use the molar ratio for that. It's a 2 to 1. Now I'm at moles of H2SO4. Now we are looking for liters. So again, I can use my molarity equation. Now that I have moles of H2SO4 that I get here, I could do the molarity equation again. So now I have the molarity, it's 10th molar. I have the moles, and I can solve for the volume. If you like to do it that way, go for it in your notes. I prefer to keep going so that it's just one setup. I'm looking for volume for liters, right? So I have moles right now, so I'm going to put moles on the bottom here so they cancel. And I put liters here because that's what I want. And now I need to link between moles and liters of a solution. To do that, you use the molarity. You just have to be careful, though. This says 0.1 moles per liter. So that means 0.1 moles for every 1 liter. 0.1 moles for every 1 liter. So where are my moles? My moles are here. So 0.1 moles for every 1 liter. So you have to watch out that you put the 0.1 here and the 1 there, not opposite. Again, if this bothers you, you do it with the molarity equation, like here. So you do it in your notes the same way that you would want to do it on a test. That way, when you look back at your notes, it makes more sense to you. So altogether, we end up with 0.04, need 36638 liters. And that's our answer. All right, last problem, last but not least. This is a fun problem. It says iron ore. Remember we talked about ores? So ores are where you find a metal oxide with some impurities. So an iron ore contains a mixture of Fe2+ and Fe3+ ions. Such an ore can be analyzed by dissolving it in an acidic solution, and then, that should say then, titrating it with KMnO4. The MnO4 minus, the permanganate ion that's from the KMnO4, is then reduced to Mn2+, and Fe2+ is oxidized to Fe3+. A sample of ore weighing 0.3500 grams was dissolved in an acidic solution, and all the iron was reduced to Fe2+. Then the solution was titrated with 1.621 times 10 to the negative second molar to KMnO4 solution. The titration required 41.56 milliliters of permanganate solution to reach the pink end point. Determine the mass percent of iron in the ore. Wow, so there's a lot going on in here. Let's think about what we're trying to do here. So they're telling us we have this ore. So let's call this the ore. And the ore is 0.3500 grams total, right? That ore contains, it says, Fe2+ and Fe3+, and some other impurities. Some other things, okay? You can just write other there. So what are we trying to find? We're trying to find the mass percent of iron in the ore. Mass percent of iron in the ore. So we're trying to find the percent of iron in this ore. How much of it is iron and how much of it is impurities or oxide or whatever it is. So to find percent of anything, you take the mass of that substance you're interested in, divide by the total times 100%, right? So it's going to be the mass of the Fe in this ore divided by the total mass times 100%. Okay, good. Do we have the mass of the iron? I don't see the mass of the iron anywhere, so we'll hold on to that. Do we have the total mass of the ore? Yes, we do. It's 0.3500 grams, right? So 0.3500 grams. So all we're missing is just the mass of the iron so that we can put it here, right? Great, we're like halfway done. We just need one number there. So how do we get the mass of the iron? So let's read it a little bit more carefully. So it says that they're going to take this ore and dissolve it in an acidic solution. Then they're going to titrate it with KMnO4. Okay. They're saying the permanganate, the MnO4 minus from the KMnO4, is reduced to Mn2+. So let me write that down. So the MnO4 minus is reduced to Mn2+. Okay, good. And the Fe2+ is oxidized to Fe3+. So the Fe2+ is oxidized to Fe3 plus. Okay. So we're taking the permanganate and the Fe2 plus. So we're reacting the permanganate with this right here, turning it into Fe3 plus. So, and another way to write this, I could have written it as MnO4 minus plus the Fe2 plus yields Mn2 plus Fe3 plus, right? It's a whole one reaction. I just kind of split it up into the oxidation and reduction half reaction. So that's my equation, right? Let's balance it. Let's balance my equation. So this seems like it's a redox reaction, so we're going to balance it. On the test, you would not have to balance something like that. Remember, you don't have to worry about the oxygens and the hydrogens, but we'll do it in class here. So Fe2 plus Fe3 plus, I'm going to balance it by just putting an electron there. See how easy it is? Now let's take a look at this one. Mn, so the non-oxygen hydrogens are balanced. Now we're going to do oxygens, 4 here, none there, so we'll put 4H2O. Then hydrogens, I need 8 H pluses. And then the electrons, let's see, this is a +2 total, this is a +7 total, so I need 5 electrons. Then the next step is to equalize your number of electrons here and there, so that means we need to multiply this by 5. So it's 5 Fe2 plus yields 5 Fe3 plus 5 electrons. I'm going to rewrite that. So 8H plus Mn O4 minus plus 5 Fe2 plus yields Mn2 plus 4H2O plus 5 Fe3 plus 5 electrons. My electrons cancel, right? So this cancels with this. So I'm just gonna ignore that here. And this is my equation, right? So let me see if I can erase this one so it looks a little bit nicer. That's my equation. And so now, oh, I don't know why it keeps reappearing. Need to practice erasing. Okay. Anyway, so this is my equation, my balanced equation right here. And let's go ahead and write down what we know. So we are given that we are using 1.621 times 10 to the negative second molar of the KMnO4. Where is the KMnO4 here? It's this one. What about the potassium? It's a spectator ion. So this is 1.621 times 10 to the negative second. I'm going to write it as moles per liter. We know that we're going to use 41.56 milliliters. So that would be 0.04156 liters. And what were we trying to find again? We were trying to find the mass of the Fe. So we're trying to find the mass of the Fe. Is it this Fe3 plus or is it this Fe2 plus? It doesn't matter, right? They're the same mass. The difference between Fe2 plus and Fe3 plus is like an electron. So whichever one you prefer, it doesn't really matter. Pick one. Just because I don't have room here, I'm just going to say there. That's what I'm solving for, is the grams there. So let's do that. So I'm going to find the moles of the one I have information about first. So 0.04156 liters of the MnO4 minus. Put liters on the bottom, moles on top. And this tells me that for every 1 liter, there's 1.621 times 10 to the negative second moles. So 1.621 times 10 to the negative second moles for every 1 liter. Now, if you don't like this, remember, you can use the molarity equation, right? We have the molarity, we have the volume, you can solve for the moles. Once we have the moles of the permanganate, we go to moles of whatever we want. So either the Fe2 plus or the Fe3 plus, either one, doesn't really matter. I'll just stick with Fe3 plus here. So moles of MnO4 minus, moles of the Fe3 plus, and it is a 5 to 1. And now that I have moles, we can go to grams. All right, where do we get the molar mass of Fe3 plus? Well, remember, whether it's Fe neutral or Fe2 plus or Fe3 plus, the difference is just a couple of electrons, right? So it's the same molar mass. We're really, really close. Like, I mean, with 6 Figs, it's going to be the same, right? So just the molar mass of iron in general. And that gives me 0.188 grams of Fe3 plus, right? Again, the iron in this ore is Fe3 plus or 2 plus or whatever it is, does not matter. You can, the mass of Fe2 plus, the mass of Fe, the mass of Fe3 plus is going to be the same, just a couple of electrons difference. So now that we got this mass of iron, we can plug that back in to our original equation here, 0.188 grams, and we can solve for the percent. It ends up being 53.7%. Isn't that cool? So, you know, they give you lots of information. You have to do lots of stuff, but it's really a simple problem. It's just, you know, the percent of iron, right? It's pretty simple, but to get to this simple thing, you got to do a lot of steps. They also complicate things with like putting really hard numbers to, you know, deal with. And so don't let the numbers distract you. Think in terms of words as opposed to numbers. So think of, I have a molarity. When I read problems like this, I actually read them without the numbers. So as I'm reading this, I read the numbers for you guys. But when I'm reading this, I say a sample of ore weighing some mass, or some grams, was dissolved in acidic solution, blah, blah, blah. And then I say titrated with molarity or concentration or something like that. I don't actually say the number. And then I read this and I say titrated required. Oh, they give us the volume. So in my mind, as I'm reading this, like if I were taking a test, I read it with words. I say, oh, this is a concentration. This is a volume. This is a mass. I don't actually read the numbers because sometimes when they're complicated numbers, they actually distract me. So that's a tip that you can use. Now, this is, like I said, a really kind of long problem, but if this was on the test, they would have had to balance this out for you already. So you did not have to do this middle part that's right here. They would have given you this equation to start with. So you'd still have to figure this blue part out. You'd have to figure this red part out, but not the balancing here.